Hello, my name is Nicholas, and this is my video presentation of Lab 5 on magnetic braking through Faraday. The purpose of this lab is to collect observational data of the magnet and tube, model the magnet/tube interaction through code, and then compare your computed predictions with your observed data. And a little preview of the results. The real value we have is 1.22 seconds, and then the computational value is 1.185 seconds. Fundamental physics concepts that we used throughout this lab was Faraday's law, Biot-Savart law, Newton's second law, Newton's third law. Lab procedure. So we have our initial measurements of the aluminum foil that we used, and also the bar magnet, and then our mu. We had to recalculate that. We didn't use the same one from lab 3. And then the surroundings, everything else besides the foil and the magnet. And then the procedures for the setup was label the north pole of the bar magnet, hold the tube vertically, record a video while dropping the bar magnet through the top of the tube, and then record the results and repeat 5 times. Lab questions. We can't use a Faroese tube, for example, a steel pipe. This is because the tube has iron in it, which affects magnetic fields and induces a current. Second question, how does this compare to a magnet falling in free space without a tube? A magnet in free space would be faster because the magnet would be slowed throughout the aluminum tube, according to Lenz's law. And then this is our code for our initial setup. So we have our tube measurements on the top and then our magnet on the bottom, using the mu that we recalculated. And for our second slide, we have the code for magnetic field and magnetic flux on the bottom. Then for code part 3, this is our simulation for the loop that occurred during the lab. So on the left we have the code for magnetic force, and then on the right we have our gravitational force, net force, and velocity and position. And some results. So looking at the picture in the top right, we can see the red part of the magnet falling down clockwise because the magnet is making a magnetic field downwards. And then the blue part of the magnet is the opposing magnetic field from the magnet falling and causing it to go in the clockwise direction. And then looking at the graph on the bottom right, our velocity time graph, there seems to be two major parts of the velocity time graph. The downward part of the slope is created because the force of the gravity is stronger than the magnetic force. And then the constant part of the graph is created because the magnet has a constant velocity during that time. And our results again, our experimental time for the magnet through the tube was 1.22 seconds, and our computed time in the tube was 1.185 seconds. Here we can see that we have values really similar to each other, which is a good indication that we did it correct. What would happen if the magnet direction was reversed? The time would not be affected/changed, but however, all the directions of the magnetic field and currents would be reversed. And then our after lab discussions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The magnet would have a slower falling rate, because the magnetic force and current would increase due to a larger counteracting gravity. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? So this would have the opposite effect to the answer in the first question. There would be more counteracting gravity, less current and magnetic force, and the magnet would fall faster. And then this concludes my video presentation of Lab 5. Thank you.